Section 1 Introduction. In the world of data modeling, deep generative models like diffusion models and Poisson flow generative models are becoming more prominent. These models use processes that gradually modify a straightforward distribution, like a Gaussian in diffusion models, into a more complex one by solving differential equations. This process is directed by vector fields, or drifts, predicted by neural networks. However, the process often takes quite a bit of time, and it's challenging to improve the quality of the output without increasing the time required. There are two main types of samplers for simulating these processes. First, we have ODE samplers, which are deterministic after the initial randomization. The other category includes SDE samplers, where the generative trajectories are stochastic, meaning they are driven by random variables. Both ODE and SDE have their strengths. ODE samplers make fewer errors in discretization, the process of dividing a continuous space into distinct units, allowing for decent sample quality even with larger steps, thus requiring fewer evaluations. However, the quality of these models does plateau quickly. SDE samplers, on the other hand, deliver better quality when they have more time to run, but this comes at the cost of extended sampling time. We've studied the performance of SDE samplers and found that their stochastic nature helps to contract the total error, which is a combination of the discretization error along the trajectory and the approximation error of the learned neural network compared to the true drift. This error reduction is especially noticeable when there are many function evaluations, small discretization steps. Essentially, the randomness of SDE allows it to forget previous errors, which explains why SDE works better in this high function evaluation regime. Drawing on these insights, we've developed a new sampling algorithm that we're calling Restart. It combines the benefits of both ODE and SDE by alternating two subroutines: a forward process that adds substantial noise, which is like restarting the original backward process, and a backward process that runs the backward ODE. By repeating these two steps multiple times, we're able to reduce accumulated errors more effectively, while also minimizing the discretization errors. To enhance this effect, we usually place the restart interval towards the end of the simulation, where the accumulated error is greater. We've tested Restart extensively and found that it consistently surpasses previous ODE and SDE solvers in both quality and speed across different function evaluations, datasets, and pre-trained models. Specifically, Restart can perform the same task as the previous best SDEs but with 10 times fewer steps, achieving the same quality of results. Restart also outperforms ODE solvers even when the number of function evaluations is small. When applied to previous high-performing pre-trained models, Restart further improves performance, yielding exceptional results. We've even successfully applied Restart to practical applications, such as the text-to-image stable diffusion model. In summary, our contributions are threefold. First, we've explored and theoretically validated the contraction effect of stochasticity in ODE and SDE solvers. Second, we've developed the Restart sampling algorithm, which effectively utilizes this contraction effect for faster sampling and superior results. Finally, our experiments have confirmed the theoretical findings, showing that Restart performs better than previous samplers in terms of both quality and speed. Section Summary. Deep generative models based on differential equations, such as diffusion models and Poisson flow generative models, have been successful in modeling high-dimensional data. These models use neural networks to predict vector fields that drive the evolution of the differential equations. Previous samplers for simulating these processes can be categorized into ODE samplers, which are deterministic, and SDE samplers, which are stochastic. We propose a novel sampling algorithm called Restart that combines the advantages of both ODE and SDE, resulting in improved sample quality and faster sampling times. Section 2 Background on generative models with differential equations. We're going to explain some foundational concepts related to generative models that use differential equations. Many successful generative models borrow from physics, with diffusion models and Poisson flow generative models being notable examples. These models work through a two-step process: the forward process, which shapes the data distribution into a smooth distribution of choice, and the backward process, which gradually reverses the forward process. To illustrate, consider diffusion models, which use a forward process called the diffusion process. Here's how it works. Imagine we have a noise schedule, symbolized by sigma t, which increases as time progresses. There's also a standard Wiener process, a kind of mathematical construction used in probability theory and statistics, symbolized by w_t. The forward process in the diffusion model involves the interaction of these two factors, with some additional math to normalize the values. This process has no learned parameters, which means it's entirely predetermined. What's important to understand is that the distribution of data at any given time, t, is a mix of the original data distribution, p_0, or p_data, and a Gaussian kernel, a statistical function used to smooth the data. As time progresses and t becomes larger, this distribution becomes increasingly Gaussian-like. Once we've transformed our data through the forward process, we can sample our diffusion model. This is done either through a backward process that relies on a stochastic differential equation, SDE, or an equivalent ordinary differential equation, ODE. Both of these processes essentially reverse the forward process, gradually turning our smooth, Gaussian-like distribution back into our original data distribution. To implement this in real-world systems, we often train a neural network to estimate a certain score for each data point at a given time, which is used to guide the backward process. We call this the score field. After the score field is computed, it's plugged into the backward SDE or ODE to generate samples. Recently, work inspired by the field of electrostatics has not only contested but also integrated diffusion models. These include the Poisson flow generative models, PFGMs, which have shown improvements in generating images and antibodies. The idea here is to think of data as electric charges in an expanded space, with the generation process mimicking the behavior of electric field lines. Similar to diffusion models, PFGMs use a neural network to approximate the electric field in this expanded space. Section summary. Many successful generative models are based on physical processes, such as diffusion models and Poisson flow generative models. These models involve a forward process that transforms the data distribution into a smooth distribution, and a backward process that reverses the forward process. For example, in diffusion models, the forward process is a diffusion process with no learned parameters, and the backward process is a reverse-time stochastic differential equation or an ordinary differential equation. These models have been enhanced by recent work inspired by electrostatics, which interprets data as electric charges and simulates differential equations defined by electric field lines. Section 3. Explaining SDE and ODE performance regimes. In this section, we dive into the performance differences of ordinary differential equation, ODE, and stochastic differential equation, SDE, samplers in the context of generative models. When simulating these models, we often use numerical solvers like Euler or Hume's second method for ODEs, and the Euler-Maruyama method for SDEs. The efficiency of these methods is evaluated based on two key metrics. 1. The quality and variety of generated samples. We use the Fréchet inception distance, FID, to measure this, where lower FID means a closer match between generated and actual data distributions. 2. The speed of sampling, determined by the number of function evaluations, NFE. It's worth noting that if we try to speed up the process by reducing the NFE, the FID score typically worsens, because the larger steps in numerical solvers can increase the discrepancy between our mathematical model and the real world, or the discretization error. That being said, ODE and SDE samplers show different patterns. For instance, ODE samplers can achieve good sample quality with limited NFEs, but don't improve much when the NFE increases. On the other hand, while SDE samplers struggle with small NFEs, they excel in the high NFE regime. Here's why. ODEs generally have smaller discretization errors than SDEs. This is because, with the same order of numerical solvers, the first-order Euler method for ODE results in a local error proportional to the square of the step size, whereas for SDEs the local error is proportional to the square root of the cube of the step size. Because the latter error is significantly larger, SDE simulations usually show higher sampling errors than ODEs, hence the better sample quality of ODEs with larger step sizes in the low NFE regime. However, in the high NFE regime, the step size shrinks and discretization errors become less significant for both ODEs and SDEs. Instead, what dominates is the approximation error, the error arising from an inaccurate estimation of the underlying vector field by the neural network. We denote the discretized ODE and SDE using the learned field as ODE_theta and SDE_theta, respectively. Our theorem evaluates the total errors from simulating these within a certain time interval. It shows that the inherent randomness of SDEs helps to reduce these initial errors, but at the cost of larger additional sampling error. This results in a smaller upper bound on the total error as the step size approaches 0, which pertains to the high NFE regime. In essence, the random, minor noise added at each step in SDEs can push the generated distribution and the true distribution towards each other, reducing some of the initial accumulated error. Even though SDEs have higher discretization error than ODEs, this contraction effect on the initial error becomes the dominant factor impacting the upper bound in the large NFE regime where the step size is small. This brings up an interesting question. Can we develop a sampling algorithm that combines the strengths of both ODE and SDE samplers? That is, can we create a sampler that maintains a similar level of discretization error as an ODE, while also taking advantage of the contraction effects induced by the randomness in SDEs? We'll explore this idea in the next section, introducing a new algorithm called restart, which is designed to achieve both of these goals simultaneously. Section summary. When using numerical solvers to sample from generative models, ODE samplers perform better than SDE samplers in the small NFE regime due to lower discretization error. However, in the large NFE regime, SDE samplers outperform ODE samplers because the contraction effect of SDEs dominates over discretization errors. To combine the strengths of both samplers, a novel algorithm called restart is introduced in the next section. Section 4. Harnessing stochasticity with restart. In this section, we discuss our proposed method called the restart sampling algorithm. This algorithm works by introducing randomness during the sampling process, which speeds up the generation of samples. We begin by explaining how the algorithm functions and then move on to offer a theoretical understanding of it. As per our findings, restart offers an improved Wasserstein upper bound compared to stochastic differential equations, SDE, and ordinary differential equations, ODE. This improved performance is due to the enhanced contraction effects of restart. In our restart algorithm, the simulation goes through a series of repetitive back-and-forth steps within a certain time interval. This interval is set within the simulation of the original backward ODE, which we refer to as the main backward process. This process runs from the end to the beginning of the time period under consideration. We also have another process known as the restart backward process, which operates within the same time interval. It's called the restart backward process, to differentiate it from the main backward process. This new process starts with samples at the minimum time, which are generated by the main backward process. Then, we introduce a large amount of noise to transition the samples from the minimum to the maximum time. This is accomplished with the help of the forward process, which doesn't require any neural network evaluation and is generally defined by a perturbation kernel. This kernel is capable of transporting distributions from the minimum to the maximum time. For example, in diffusion models, this kernel might be represented by a normal distribution with zero mean and a variance equal to the difference of the square of the two standard deviations at the maximum and minimum times. This introduction of noise results in a more significant contraction compared to the small, continuous noise in SDEs. It's as if we're partially restarting the main backward process by extending the time. After this step, the restart algorithm simulates the backward ODE from the maximum time back to the minimum time, just like in a regular ODE. We then repeat these forward and backward steps within the time interval for a specified number of iterations to fully reap the benefits of contraction. For each iteration, we have two distinct processes. 1. The restart forward process, where the sample at the maximum time for the next iteration is obtained by adding noise to the sample at the minimum time of the current iteration. 2. The restart backward process, where the sample at the minimum time for the next iteration is obtained by running the ODE backward from the maximum time of the next iteration to the minimum time. The initial sample at the minimum time is obtained by running the ODE until the minimum time is reached. The noise added during the restart forward process is sampled from the perturbation kernel from the minimum to the maximum time. Not only does the restart algorithm introduce substantial noise during the forward process, but it also separates randomness from the ODE, resulting in an increased contraction effect, as we will show in the following subsection. For example, we chose a time interval from 0.05 to 0.3 for the VP model on the CIFAR10 dataset. By repeatedly introducing noise in the forward process, we can effectively reduce the errors that have accumulated during the simulation until the maximum time. Furthermore, the restart algorithm doesn't suffer from large discretization errors because it primarily follows the ODE in the restart backward process. As a result, the restart algorithm can reduce the total sampling errors even when the number of function evaluations is small. Detailed instructions for the restart sampling process can be found in the appendix. Section summary. In this section, the authors introduce the restart sampling algorithm, which incorporates stochasticity during sampling while enabling fast generation. The algorithm involves repeated back-and-forth steps within a predefined time interval, where a large noise is added to transit the samples. This noise induces a more significant contraction compared to the small interleaved noise in other methods, resulting in reduced sampling errors. Section 4.2 Analysis. We're now moving on to analyze the restart algorithm. In line with our prior work, we demonstrate how this algorithm substantially reduces the contracted error in the upper bound of the Wasserstein distance compared to the stochastic differential equation or SDE method. This efficiency stems from two factors: the segregation of noise from the drift and the considerable amount of noise introduced in the restart process. Moreover, by running the restart cycle multiple times, we can significantly decrease the initial accumulated error. To illustrate this, we reference the intermediate distribution that results from the ith restart iteration, using discretized trajectories and the learned field S, with a subscript, theta. The next theorem, though informal, provides a practical understanding. Under the same conditions as the previous theorem, if we assume that k is less than or equal to a universal constant, c, divided by the product of L_2 feet and the difference between the maximum and minimum time, we can then derive a few relationships. First, the total error, represented by the first Wasserstein distance of the kth restart iteration and the distribution at the minimum time, is less than or equal to an upper bound. This upper bound is the product of a constant b, and the difference in total variation, tv, between the initial restart iteration and the distribution at the maximum time, reduced by a factor, 1 lambda, raised to the power, k. The error is further compounded by an additional term related to the number of iterations, k, and the approximation and discretization errors, scaled by the difference between the maximum and minimum time. Here, lambda is a contraction factor less than 1. To determine this total error, we introduce a helper process, q, that starts from the true distribution at the maximum time and performs the restart iterations. This process only differs from the initial restart iteration in its starting distribution at the maximum time. We then use a mathematical trick called the triangular inequality to encapsulate the total error. The total error is less than or equal to the sum of the contracted error, the first Wasserstein distance between the kth restart iteration and q at the minimum time, and the additional sampling error, the first Wasserstein distance between q and the distribution at the minimum time. To confine the contracted error, we devise a coupling process between two independent trajectories sampled from the initial restart iteration and q at the minimum time. The Gaussian noise added in each restart iteration aims to increase the likelihood of these trajectories mapping to the same point, thereby maximizing the mixing rate in total variation. Once converged, the two processes continue under the same Gaussian noise and stay converged since their drifts are identical. Finally, we convert the total variation bound to a first Wasserstein distance bound by multiplying by b. The additional sampling error aligns with the ODE analysis in our prior theorem. Since the noise injection and ODE simulation stages are separate, we avoid the higher discretization error of SDE. The first part of the right-hand side encapsulates the contraction on the initial error at the maximum time, while the second part pertains to the additional sampling error of the ordinary differential equation or ODE that accrues over repeated restart iterations. From this, we observe three key points. Firstly, each restart iteration has a smaller contraction factor, 1 lambda, than the SDE because the restart separates the large additive noise from the ODE. Secondly, the restart backward process has the same order of discretization error as the ODE, in contrast to the square root of the discretization error in the SDE, meaning the restart requires less computations due to this lower discretization error. Lastly, the contracted error decreases exponentially as we increase the number of iterations, while the additional error increases linearly. This suggests a delicate balance when choosing the number of iterations. If the initial error at the maximum time is significantly larger than the incurred error during the repetitive backward process from the maximum to the minimum time, it would be beneficial to opt for a larger number of iterations. To support our claims, we will provide empirical evidence in the next section. We'll compare the upper bounds on errors of different methods and show that the restart algorithm indeed produces a smaller total error due to its superior contraction effects. Section Summary. The section presents a theoretical analysis of the restart algorithm, showing that it achieves a smaller contracted error in the Wasserstein upper bound compared to the SDE algorithm. The analysis demonstrates that the repetition of the restart cycle leads to an enhanced reduction in the initial accumulated error. The section also highlights the advantages of the restart algorithm, such as separating noise from the drift and allowing for smaller NFE, number of function evaluations, due to ODE-level discretization error. Empirical evidence is provided to validate the theoretical findings. Section 4.3 Practical Considerations. Section 4.3 Practical Considerations. The restart algorithm allows for multiple customization options, such as the time interval and the number of iterations. This section aims to provide guidance on parameter selection, considering the complexity of the generative modeling tasks and the capabilities of the neural network. We also propose a layered, multi-level restart method to further reduce simulation errors throughout the trajectory for more complex tasks. When should we use the restart function? Theoretical evidence suggests that the restart algorithm effectively shrinks the accumulated error at the final point in time by acting as a tightening factor on the upper limit in the Wasserstein space. Inspired by these findings, we recommend positioning the restart interval towards the end of the main backward process where the accumulated error tends to be greater. Furthermore, our practical observations suggest that a larger time interval is more beneficial for weaker or smaller architectures or more difficult datasets. Even though a longer time interval adds to the sampling error, the benefits of error reduction far outweigh the additional errors introduced, aligning with our theoretical predictions. However, we acknowledge that more research is needed to develop structured methods for optimal time interval selection. In terms of multi-level restart, for tasks that lead to considerable approximation errors, the backward trajectories may start deviating from the true path early on. To prevent the differential equation simulation from veering off course too soon, we propose using multiple restart intervals in the backward process, in addition to the one positioned towards the end. From our observations, a single-level restart is adequate for simpler datasets like CIFAR10. However, for more challenging datasets, like ImageNet, implementing a multi-level restart improves performance. Section summary. The restart algorithm allows for flexibility in parameter selection, such as the time interval and number of restart iterations. Theoretical findings suggest placing the restart interval towards the end of the backward process, where the accumulated error is higher, and a larger time interval is more beneficial for weaker architectures or challenging datasets. For tasks with significant approximation errors, implementing multiple restart intervals, including one towards the end, improves performance, especially for more challenging datasets like ImageNet. Section 5 Experiments. In this section, we first put our theoretical findings to the test, focusing on the topic of Wasserstein upper limits. Following that, we assess various sampling techniques using widely accepted image generation benchmarks, such as CIFAR10 and ImageNet with 64 by 64 resolution. Lastly, we apply the restart method to the task of text-to-image generation. We use a pre-existing stable diffusion model that's been pre-trained on a dataset called LAION5B, which uses images at a resolution of 512 by 512 pixels. A key part of our research is analyzing the trade-off between what we've termed additional sampling error and contracted error. To evaluate this, we developed a sampling method called restart. Our findings show that restart has a greater effect on reducing contracted error and lesser effect on increasing additional sampling error, compared to a method known as stochastic differential equations, SDE. To back up our theoretical analysis, we performed a practical test. We created a 20-dimensional dataset with 2,000 data points, which were selected from a mix of Gaussian distributions. We used a 4-layer multi-layer perceptron (MLP) model to approximate a field which we termed score field. We compared three methods: an ordinary differential equation (ODE) method, the SDE method, and our proposed restart method. Each method was used within a specific range of time values between 1.0 and 1.5. We used the ODE method for any processes outside of this time range. To calculate different types of errors, we came up with a way to represent the data produced by each method. The first is the output from our sampler, either ODE, SDE, or restart, denoted as P. The second is an auxiliary output, denoted as Q, which starts from the true distribution at the maximum time value. The key difference between P and Q is their starting distributions at the maximum time value. The final representation is the true data distribution. Using the Wasserstein 1 distance, we were able to quantify the contracted error and additional sampling error. The total error is the Wasserstein 1 distance between the sampler output and the true data distribution. You can find more details on the dataset, the measurement used, and the model in the appendix of our paper. When we carried out the experiment, we adjusted the parameters for all three methods and calculated the total, contracted, and additional sampling errors under all parameter settings. The results are visually represented in the figures included in our paper. What we found was that the restart method consistently achieved a lower contracted error for any given level of additional sampling error, compared to both the ODE and SDE methods. This confirms our theoretical predictions. Furthermore, we noticed that the restart method recorded a smaller total error within the additional sampling error range of 0.8 to 0.85. During this range, restart also showed a strictly reduced contracted error. This supports our theory that the restart method can offer a smaller total error due to its stronger effect on contraction. Ultimately, the restart method also offered a better balance between efficiency and quality. It achieved a lower total error at a given number of function evaluations. Section summary. In this section, the authors first verify their theoretical analysis on Wasserstein upper bounds and then evaluate the performance of different sampling algorithms on image generation benchmarks. They also employ the restart method on text-to-image generation and compare its contraction effect and additional sampling error to the SDE method. The authors conduct a synthetic experiment to further verify the relative values of different error types and show that the restart method consistently achieves lower contracted error and smaller total error compared to the ODE and SDE methods. Section 5.2 Experiments on Standard Benchmarks. We conducted experiments on standard benchmarks to assess the quality of samples and the speed of inference. We utilized the FID score, which should ideally be lower, on 50K samples and the number of function evaluations, NFE, as metrics for these evaluations. We used pre-trained VP, EDM, PFGM++ models on CIFAR10 or ImageNet 64x64 datasets. We utilized the EDM discretization scheme during sampling. For our proposed restart sampler, we had to select hyperparameters including the number of steps in the main and restart backward processes, the number of restart iterations, K, and the time interval with minimum, T_min, and maximum, T_max, values. We selected these time intervals from the list of time steps in the EDM discretization scheme, which contained 18 steps. For example, with CIFAR10, VP, and NFE equals 75, we chose T_min equals 0.06, T_max equals 0.30, and K equals 10. In this case, 0.30, 0.06 was the 12th, 14th time step in the EDM scheme. We also used the EDM scheme for the restart backward process within the T_min and T_max interval. Furthermore, we employed a multi-level restart strategy to lessen the error in early time steps, particularly for the more complex ImageNet 64x64. Detailed restart configurations are provided in the appendix. For stochastic differential equations, SDE, we made comparisons with the previously best-performing stochastic samplers. We used their optimal hyperparameters for each dataset and reported the FID scores of the adaptive SDE on CIFAR10, VP. Ordinary differential equation, ODE, samplers were compared using Hume's second-order method, which strikes a good balance between discretization errors and NFE. To ensure a fair comparison, we incorporated Hume's method in the main and restart backward processes in restart. While we could have utilized faster, more complex ODE solvers like the DPM solver to boost restart, we chose to leave this as a point of future exploration. We recorded the FID score against NFE in diagrams and tables on CIFAR10 and ImageNet 64x64 with EDM. The results show that restart is superior to other SDE or ODE samplers in terms of sample quality and speed, across different datasets and models. Remarkably, restart provided a 10-fold and 2-fold acceleration compared to the best previous SDE results on CIFAR10, VP, and ImageNet 64x64, EDM, respectively, given the same FID score. Stronger models like EDM and PFGM++ saw further improvements with restart over the ODE baseline on CIFAR10. However, the improved SDE decreased the performance of EDM. This suggests that restart incorporates randomness more effectively. Impressively, restart achieved new best FID scores for UNet architectures without additional training, particularly 1.36 on class-conditional ImageNet 64x64 with EDM and 1.88 on unconditional CIFAR10 with PFGM++. The theorem demonstrates that each restart iteration lessens the contracted errors while increasing the additional sampling errors in the backward process. We investigated the number of restart iterations K on CIFAR10 and discovered that the FID score initially improves and later deteriorates with increasing iterations K. This supports the theoretical analysis that sampling errors will ultimately outweigh the benefits of contraction as K increases. Thus, for weaker or smaller architectures, we should apply greater restart strength, i.e., larger K, and the opposite for larger or stronger ones. Section summary. The experiments conducted on standard benchmarks involved evaluating the sample quality and inference speed using the FID score and the number of function evaluations. The hyperparameters for the proposed restart sampler included the number of steps in the main, restart backward processes, the number of restart iterations, and the time interval. The restart sampler outperformed other SDE or ODE samplers in terms of balancing quality and speed, achieving a significant acceleration compared to previous results. It also established new state-of-the-art FID scores for certain architectures without additional training. Section 5.3 Experiments on large-scale text-to-image model. We've extended our use of the restart technique to the Stable Diffusion version 1.51 text-to-image model, which was initially trained on the expansive LAION5B dataset at a 512 by 512 pixel resolution. For sampling, we utilized the widespread practice of classifier-free guidance, which involves two function evaluations at each step, the conditional and unconditional predictions. In terms of evaluation, we used the COCO validation set. We assessed the alignment between the text and generated image using the CLIP score with the open-sourced VIT-G14, and we gauged diversity through the FID score. Furthermore, we examined visual quality via the aesthetic score, as judged by the LAION Aesthetics Predictor V2. To calculate these metrics, we randomly picked 5,000 captions from the validation set and plotted the trade-off curves between CLIP aesthetic scores and the FID score. We varied the classifier free guidance weight, W, among 2, 3, 5, and 8. We compared our approach with the conventional ODE sampler DDIM and the stochastic sampler DDPM. For restart, we used the DDIM solver with 30 steps in the main backward process and the Hewn method for the restart backward process. We found the Hewn method outperformed DDIM for the restart process. We also used different sets of hyperparameters for each guidance weight. For example, when the guidance weight was 8, we set the minimum and maximum time values, T_min and T_max, to 0.1 and 2 respectively, with k equal to 2 and 10 steps in the restart backward process. We have provided the detailed configuration of restart and results of the Hewn method in the appendix. Our results demonstrate that restart generally achieves better FID scores, given the same CLIP aesthetic scores, and this was accomplished with only 132 function evaluations, or 66 sampling steps. Remarkably, restart outperforms other samplers in terms of lower FID scores when CLIP aesthetic scores are high, which correspond to larger guidance weight values. Conversely, restart also tends to achieve better text-image alignment and visual quality for the same FID. Interestingly, we noticed that the DDPM method achieves similar FID scores to restart when CLIP aesthetic scores are low. However, restart does this more efficiently. This suggests that restart manages to balance diversity, as represented by the FID score, against text-image alignment, CLIP score, or visual quality, aesthetic score, more effectively than previous samplers. To give a visual comparison, we generated images using restart, DDIM, and DDPM with a guidance weight of 8. Compared to DDIM, restart was able to generate images with better detail and visual quality. For instance, the DDIM model's depiction of duck legs was less accurate. Compared to DDPM, restart produced more realistic images, like the astronaut for instance. You can find more samples of text-to-image results in the appendix. Section Summary. In this section, the authors conduct experiments on a large-scale text-to-image model using the restart method. They evaluate the model's performance using various metrics such as CLIP score, FID score, and aesthetic score. The results show that restart achieves better FID scores while maintaining high CLIP aesthetic scores, indicating a better balance between diversity and text-image alignment, visual quality compared to other samplers. The authors also provide visual comparisons of images generated by restart, DDIM, and DDPM, demonstrating that restart produces images with superior details and visual quality.